Hello, today we're looking at the final topic in sequences and series, and likely the final topic you'll see in Calculus 2. And so these are Taylor series. So you may recall from last time we did Taylor's polynomial, and actually it's probably worth just having a quick reminder of what they are, because the Taylor series are very similar. So you'll recall the Taylor polynomial, it's a polynomial of degree n of some function centered x equals c is given by this equation. And we have this first term, f of c, the second term is f prime of c multiplied by x minus c. Then we take the second derivative at c divided by 2 factorial x minus c squared, and so on and so on. And our general final term is the nth derivative of c divided by n factorial, and that's multiplied by x minus c to the n. And similarly, we have the Maclaurin polynomial, which is just where we set c equal to 0. Okay, so this is a polynomial of degree n, and it terminates, it stops at that highest degree n. Well, a Taylor series is going to look very similar. We can condense it down into summation notation, but we still have this nth derivative evaluated at c, and we still divide by this n factorial, and we have the x minus c to the n, and it's the sum of all these terms, but now you'll notice the index here says that this goes from n equals 0 to infinity. In other words, it's an infinite series, whereas previously with the Taylor polynomial, we curtail the polynomial at the degree n. This is just going to keep going and going as an infinite series. Just as we saw previously, if we set c equal to 0, we replace a c with a 0 here, we get a Maclaurin series, and of course if we set the c equal to 0 here, the x minus c just becomes x, so this is a Maclaurin series. Again, that's just a special case of the Taylor series with c equal to 0. Okay, so this is our formula for Taylor series. Let's take a simple example, make it a Maclaurin series because that's nice and simple, and we'll take our function to be sine x, which is pretty easy to differentiate. And just as before, we're going to differentiate it a few times. So in fact, let's take 10 derivatives here. And of course it's very easy to do. The first derivative is cosine, then we switch to negative sine, negative cosine, but of course this starts repeating. We get back to sine as the fourth derivative, and then it just kind of repeats itself. So we can quickly take lots of derivatives. And then because we're looking at a Maclaurin series, we have to plug in the value 0. So we find f of 0 is 0, f prime of 0 is 1, double prime is 0, triple prime is negative 1. And again, this is going to repeat itself. Okay, so we're going to get 0, 1, 0, negative 1, just kind of repeating. And if we remember the formula, let's just bring that in here. These are going to be the coefficients when divided by their appropriate factorials. So this is going to give us that the Maclaurin series for sine x is this. So obviously we have a bunch of terms. In fact, the even powered terms of x are not there because they all have coefficient 0. And then the odd powers of x are all going to alternate with a 1, negative 1, 1, negative 1. And as I say, we need those factorials in the denominator. So that is the Maclaurin series for sine x. And again, you'll notice this is an infinite series now. We have the dot, 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 which tells us this keeps going. And this gives us the series for sine x. Here are a few others that are well known and quite common. I have about 6 here. There are a couple more in the book if you want to look at those. So e to the x, and we saw this when we did the Taylor polynomials, all the coefficients are just 1, so it's just 1 plus x squared over 2 factorial and so on. Sine x, that's the one we just saw, and you can probably kind of guess how the cosine might work. It's going to look very similar with the 1, negative 1, 1, negative 1, except the zeros would be for the odd powers now, so we're just left with the even powers, as we can see here. And then there's a couple more, the natural log of x, 1 over 1 minus x, and arctan x. I'll say these are just a few common ones that we might want to use, and we can kind of extend this. We can use the ones we already know to find others that we don't, and we'll see that in a second. Now, one more thing about these series. We saw when we did power series that the power series converge for certain values of x. In some cases they might converge for all x. In certain cases they might just converge for some finite range. And in certain cases, they only converge at a specific value. And you may recall to find the radius of convergence, we use the ratio test. So let's do that here. Okay, so the natural log of x, it's given by this formula. We had that on the page previously. And let's find the radius of convergence for this. So recall the ratio test. I guess it's been a little while, maybe we'll just bring that in here. There it is. The ratio test says we take the limit as n goes to infinity of the n plus 1th term divided by the nth term, and we're looking for when that is less than 1. Okay, so let's apply that to our series we have here. So we have minus 1 to the n plus 2 in the numerator and the x minus 1 to the n plus 1 over n plus 1, just replacing all the n's with n plus 1's, and then we just have the nth term in the denominator. Because we're inside the absolute values, the negative 1 powers can quickly disappear, and we're just left with this. That was kind of easy. And as we've seen lots of times with the ratio test, we kind of flip the bottom and we'll gather together the terms that look similar. And so we have x minus 1 to the n plus 1 and x minus 1 to the n, which hopefully you're familiar with. The n's just sort of cancel, and we're just left with an x minus 1 in the numerator. We can also take the n over n plus 1 outside the absolute value signs because they're all positive, and then we can see that the limit here, this limit as n goes to infinity of n over n plus 1 is just 1. So if this piece is going to 1, all we're left with is the absolute value of x minus 1. And remember, we're interested in when that is less than 1. That was when the ratio told us that the series converged. And so x minus 1 is less than 1. That gives us that it must be between 0 and 2. Now I haven't missed a little step here. I've gone straight to the final answer. If you try plugging in 0 for x into the original formula, you'll find it diverges, and if you plug in 2, it converges. Therefore, we have the kind of the inclusive and exclusive here. So we have the open interval on the left and the closed interval on the right. So our radius of convergence for the natural log of x is 0 to 2. And again, if you look at the table of series in the book, you'll see all the radii of convergence. Okay, so I mentioned previously that we can actually take some series that we know about and sort of combine them to get new series. And we're going to do that here. So we're going to let f of x and g of x be two power series, and then we can apply these rules. We'll assume some sort of convergence here, that they both converge for x within some range. Well, the first one says that if we sum two series, we can just sum the coefficients. So if we know that the coefficients of the f of x are the a-n's and the coefficients of the gx are the b-n's, then we can just sum those coefficients and get a new series, which would be fx plus gx, or minus. Similarly, we can multiply here. This is slightly more complicated because, of course, you have to combine the terms, and we'll see an example of that in just a second. And then finally, we have f of h of x. We can actually plug in the h of x where we had the x, and again, we'll see an example of that in a minute. It'll be fairly clear. Okay, so let's combine a couple. So we have the Taylor series for e to the x, and we have it for cosine x. Those are both from our table. And let's suppose we want to find the Taylor series for e to the x cosine x. And otherwise, we multiply these two functions on the left here. Well, if we're going to multiply the two functions on the left, we're going to multiply the two series on the right. And this is a little tricky, right? We have these two infinite series, and we will get another infinite series that are multiplied. But all we're going to do is start collecting like terms. So actually, we'll take the cosine x to be each of these, and we'll just break out the terms from the e to the x, the 1, the x, and the x squared over 2 factorial here. And then if we distribute through and start adding, I know it'll take a minute to do the algebra here, but hopefully you can see we get the 1 from kind of here, the x term we're going to get from here, we're going to get an x squared, negative x squared over 2 factorial from right here. We're also going to get an x squared over 2 factorial right here, but positive, so those two actually cancel out, which is why we don't have that kind of x squared term. But then we get an x to the 3 term, that'll come from right here and here, sort of combined together, and so on and so on. So that's going to be our series, that's how we do that. So our series for e to the x cosine x is 1 plus x minus x cubed over 3 minus x4 over 6, and so on and so on. So we've taken two very simple series and found the series of that. Notice, of course, we could have taken this function and just differentiate it a few times and find the coefficient, but hopefully it's clear to see that's going to take a lot of work. Okay, we differentiate and plug in. Well, each time we differentiate, we're using product rules, and it's going to get bigger and uglier, so that's probably all we need to do. Oh, and yes, with one more note, both e to the x and cosine x converge everywhere between negative infinity and infinity. So therefore, so does the series expansion for e to the x cosine x. Okay, let's take a couple more ways we can sort of take a series we already know and create a new one. So let's take e to the x cubed. Okay, and again, we could just take this, differentiate it lots of times, plug in, and so on and so on. But that's going to be hard work. So instead, let's take e to the x. Okay, we know that one, that's pretty simple. I should just note at this point, this again is centered at 0, so I guess it's a Maclaurin series. Keep it nice and simple. So this is e to the x. And now all we're going to do is everywhere we see an x, we're going to replace it by an x cubed. So on the left-hand side here, where we had the x cubed. So on the right-hand side, well, every time we see an x, we just throw in an x cubed. So we get 1 plus x cubed, we can get x cubed squared, get cubed, and so on and so on. And of course, that simplifies very quickly. So we have the series for e to the x cubed, which is going to be 1 plus x cubed plus x to the 6 plus x to the 9 over 3 factorial, and so on. Okay, and that's clearly much quicker than trying to differentiate the original e to the x cubed a bunch of times where we start using chain rule and product rule. This was very straightforward. We can even differentiate. Suppose we took the derivative of the left-hand side, the derivative of e to the x cubed, and we wanted a series for that. Well, then we just take the derivative on the right-hand side, the derivative of the series on the right-hand side. And to do that, we just take the derivative of each term. So the left-hand side, using a little bit of chain rule, we're going to get 3x squared e to the x cubed. And the right-hand side, well, we differentiate 1, of course we get 0, but then we differentiate x cubed, we get 3x squared, x to the 6 over 2, we get 6x to the 5 over 2 factorial, and so on and so on. Okay, so this would be the series for 3x squared e to the x cubed. Just a quick note on this, you'll notice, in fact, this is only 3x squared multiplied by what we started with. Okay, so we could also have taken this function and just multiplied it by 3x squared, and we would have got the same thing. Kind of a fun fact, there's more than one way to do these things. Okay, so we can add series, we can multiply them together, we can differentiate. We haven't seen an example, but we could also integrate. We have to be a little careful with the constant of integration there. But at this point, we've found lots of different Taylor series. And there are all these infinite series which give us the value of a function. Okay, and that's about all we have on Taylor series.